This week's subject is projectile motion. Pause the video and make a list of the important characteristics of all projectiles. Then once you've got your list, start the video up again. Okay, you're back. These are the key features. You want to review them, remind yourself, and whenever you do a problem, always check that you're following and paying attention to these features. So we have number one, the only force acting is the force of gravity. And that means there's only one acceleration, the acceleration due to gravity. And we know what that is. It's, whoops, I forgot the negative signs. Let me stop. Okay, so the acceleration due to gravity is a negative 9.80 meters per second squared, or for convenience we often use 10 meters per second squared. The fourth and often most common mistake that you'll make is that you'll mix up the x and y components. There is no acceleration in the x direction. The velocity in the x direction will be constant. It won't change. The acceleration in the y direction should never be used when you're calculating information about what happens in the x direction. Alright, now in the lab we see three distinct kinds of projectile motion. One is a projectile, well, let me get my pencil, a projectile that goes up and comes straight down, a one-dimensional problem. We've seen this before. That's not a very good scale. I'm going to stop and correct it. Okay, once again, the three distinct examples that we see in lab: the projectile that goes straight up and reaches its peak and comes back down. And if it goes up at a velocity, we'll have this going up at a velocity of 30 meters per second. I'm not going to write that in, but it rises after 1 second. So it starts out at 30 meters per second. Because of the acceleration of -10, it goes to 20 meters per second. After 2 seconds, it's 10 meters per second, and then it reaches the top. After 3 seconds, 0 meters per second, and then it comes down along the same line, -10, -20, -30. So this you should know. We've seen this many times. And then we can calculate the distances it travels during those times using our equations of motion, as we have done many times. Just for your reference, this is 35 meters, 25 meters, 40 meters, and 45 meters. Okay, now you practice. We take an object from a building that's 45 meters high, and we point the projectile launcher horizontally, and we launch the thing with a velocity. Let's launch it at 30 meters per second, horizontally. Okay, now I want you to pause the video and draw the figure, the motion diagram, showing its position and its velocity every as it falls to the ground 45 meters. Okay, you pause the video, you finish that, and you're back. If you haven't, go back and do it. Alright, here's what happens. So I chose 45 meters because I know from the previous diagram that if you start with 0 velocity, it'll in 3 seconds come down 45 meters. So I know this is going to take 3 seconds to reach the ground. And I know the horizontal velocity is 30 meters per second, and it's constant. So after the first second, let's go back to our first figure. After the first second, it's going to drop 5 meters. After the second second, it's going to drop another, oh, here's the 5 meters, another 15 meters, and then in the third second, it's going to drop 25 meters. So 5, 15, 25. You could use your equations to figure this out, but I know it well enough, and I'm taking it from this figure. So here's the motion diagram. After 1 second, it's gone 30 meters this way. I want to make sure I don't go off the page here. So, and it's fallen 5 meters. So I'm going to fall down. You see, I'm going to fall down the 5 meters and go 30 meters out. The 30 meters, it should be a little bit longer, but I'm going to go off the page if I do it all to scale. So it's come down 5 meters and it's traveled horizontally 30 meters. Why? Because the horizontal velocity is 30 meters per second and it's constant. In the next second, it's going to go another 30 meters, but this time it's going to drop 15 meters. So now it'll be down here, right, at the same height as this one. And you see these are 30-meter intervals. And so during the next second, it's going to travel another 30 meters and fall that 25 meters. So after 3 seconds, all right, now let's go back to our 45-meter building, and let's point the projectile launcher at 45 degrees. And just to keep it simple, I'm going to say that the projectile was coming out at 30 meters per second. In this case, let's just say it's a little slower. Now the velocity should be independent of angle. We saw that in lab. But just for even numbers, I'm going to have it come out at 28.2 meters per second. And the reason I do that is because when I find the components of this by taking the sine and cosine of 45 degrees, you know how to find the components, right? Okay, actually, pause the video and find the components of the velocity. Okay, you're back. You should have done this and found that they come out pretty close to 20 meters per second in both directions. The angle's 45 degrees, and those are even numbers, so the mathematics will be easy. So let me draw those in. Here's the x component. Here's the y component. And remember, the x component is going to be constant, and the y component is going to vary. So what happens after 1 second? After 1 second, the object is going to travel 20 meters downfield, and it's going to go from 20 meters per second to 10 meters per second. So it's going to go 15 meters, right? It's averaging. You can do that with your equations. So after 1 second, let's draw that in. It's going to be 20 meters here and 15 meters up. So I'm going to put the thing right about here. It's going to go right over the... So notice, I'll use the thing, it's gone 20 meters this way and 15 meters that way. Alright, see if you can finish the path of the projectile. It's going to be like this, right? Might go off the page, but squeeze it in there if you have to. Find the position and the velocities and show the vectors every second from when it leaves here to when it hits the ground, given that the ground is at the base of this building is flat, 45 meters. This is 45 degrees. This is 45 meters above the ground. Okay, so pause the video. Okay, so this is what you should have found. In the first second, the ball goes over 20 meters and up 15. In the second second, the ball goes over another 20 meters because it's going at 20 meters per second in the x direction. Goes over another 20 meters but only goes up 5. And then it comes another 20 meters, it goes down 5. Another 20 meters, it goes down 15. Another 20 meters, it goes down 25. And another 20 meters, we're off the page, and it goes down 35. So I made a mistake. I should have had the building, because this goes down 25, this goes down 35. Where am I getting the 25? Well, you should have figured that out using your equations. This goes from 20 to 30. It's averaging 25 for 1 second, so it's going to go down 25. Here it goes from 30 to 40, so it's averaging 35 during that second. It's going to go down another 35, and 25 and 35 is 60. So if I had made the building 60 meters, it would have hit the ground after 1, 2, 3, 4, 5, 6 seconds. And for the 60-meter building, it would have hit the ground. Let me just pull that over from out of here. It would have hit the ground, you know, if we do this path, right? It would have continued that way, but I'm going to pull it in here. It would have hit the ground with a horizontal velocity still of 20, but a downward velocity of minus 10, minus 20, minus 30. So the downward velocity as it hit the ground would have been a minus 30, and that would be the components of the final velocity. But let's go back to our 45 meters, and that means that it's going to take a little bit less than 6 seconds to hit the ground, and we'd have to use our kinematics equations to find out the velocity with which it hits the ground. And that might be a useful problem to do. But before I do that, let me just draw these vectors in. I was saying draw the vectors in. So on each of these, you should have a horizontal component of 20 meters per second, and a vertical component, in this case, of plus 20, plus 10, 0, minus 10, minus 20, minus 30, and then it's going to hit the ground before it gets to minus 40. So here's the problem, and I'll let you pause the video and figure it out. Find Vy final and Vx final, and the magnitude of V final and the direction of V final. That's 4 things, and the 5th thing is the time that it hits the ground. So you're pausing the video and you're going to do as much of that as you can. Okay, I don't want this to go on too long, so I'm going to kind of rush through this, and you check what you did. And if you're stuck, once you get unstuck, stop the video and try and do as much of this as you can. Okay, first thing that's simple. The Vx final is 20 meters per second, because Vx final equals Vx initial. It never changes. The Vy final we need to find. And we don't know the time, so I'm going to choose kinematics equation number 4 that says Vy final squared equals Vy initial squared plus 2 Ay delta y. Notice I'm writing this all in y because that's the direction I'm dealing with. And I chose this equation because we don't know the time. And so the Vy final is going to be the square root of all this, right? So let me see if I can do that. I'm going to pause the video and write it out. You solve that now if you didn't get that and see what you get. Okay, check your work so far. So we're using this equation to find the final y velocity. We put in Vy initial, that's this, 20 meters per second. We square it. We put in the 2ay delta y. The 2, whoops, I'm going to pause. Okay, I'm back. The reason I paused was because this should be a negative sign for both of these, and I didn't have that. So 2 times a negative 10 meters per second squared, that's the ay, minus 45 meters, that's the delta y, right? It's going down. Here's where it starts. Here's where it ends. The change in y, the final position, is 45. The initial is 0, and the initial position is plus 45. So this is a drop of 45 meters. That goes in there. When you do the math, you get 1,300 meters squared per second squared. You take the square root. It's plus or minus. Of course, we want the minus value because the y component is going down. And we can round this off for our purposes. We can just round this off to 36, negative 36 meters per second. Then we put the x component and the y component into the Pythagorean theorem of this equation for vectors, and we get that the magnitude of the velocity as it hits the ground, the instant before it hits the ground, is 41.2. So 2 more things to do. Find the angle it hits the ground at and the total time of flight from it leaves here to when it hits the ground. And then when you've got that, come back and listen to the video. Okay, let's finish up. We're getting the angle, theta. So of course that's the inverse tan of Vy over Vx minus 36 over 20 gives us a negative 60.9, or about a negative 61 degrees. That's measured right from the x-axis down counterclockwise. So that would be the angle if I drew it in. That would be the 61 degrees there, a negative 61 degrees. And the time, there's many ways of getting this, but this is, whoops, wrong. I want my laser pointer. I used this equation. And so notice what I did. I did the algebra, so see if you can follow. Subtracted V initial from both sides, divided by AY, and I get T equals V final minus V initial over AY. If you put the numbers in, this is minus 36 minus 20, that's minus 56, divided by the AY. I just used negative 10, so minus 56 divided by negative 10 is 5.6 seconds. Good, that's what we said. We said it hits the ground a little bit short of 6 seconds. We're done.